So we've talked a bit about the Ramsey numbers, and here's our definition. Remember that the Ramsey number, this is a number, and it's the smallest positive integer such that any simple graph either contains ks or its complement contains kt. We've done some examples. The very concrete one we did was we computed R33, and we found that was 6. 5 was not enough to guarantee it, but 6 was. We also found that if we take either S or T to be the number 2, we can also compute the Ramsey number. We can think of these as sort of base cases for computing Ramsey numbers using the following amazing bound. This is a great upper bound that we have for Ramsey numbers. It says that if I'm computing the Ramsey number for ST, then it's at most what I get for the Ramsey number of ST minus 1 plus the Ramsey number of S minus 1T. And this is whenever S and T are at most 2. Using this theorem, we can see that this Ramsey number is always finite because we can always apply this bound and then keep doing it until both S and T, until at least one of S and T is 2, and then we can use these base cases to get a bound for any Ramsey number. These aren't always great bounds, but they at least show us that Ramsey numbers exist and are finite. So let's try to prove this theorem. And the proof is going to be very much like the proof that you did in your homework, proving that R of 3 is equal to 6. Let's see how that goes. So again, we can think about a graph union its complement as a complete graph. And then what we're doing is we're saying, well, let's color the edges of the graph blue and the edges of its complement red. So really what we're doing is we're going to consider, well, I should say this is our proof. We're going to consider any red, blue edge coloring of Kn, where here n is going to be the right-hand side. Okay? Any red-blue edge coloring of the complete graph on that many vertices. We must show we either get a complete graph that is Ks, which is blue, or a complete graph KT, which is red. That will show that the Ramsey number here, that this, at least this value of n guarantees us one of these cases. So the Ramsey number being the smallest one will have to be at most that big. Okay. The proof, again, the structure is going to be very similar to what we did for R33. And the key there was to use the pigeonhole principle. So first what we had to do was pick a vertex. So first we're going to pick any vertex V of Kn. Okay, and now we're going to think about the edges coming out of V. Well, how many do we have? So we know that the degree of V, because we're looking at the complete graph Kn, the degree of V is n minus 1. So by the pigeonhole principle, what do we get? We either V has at least R of S minus 1 T blue edges coming out of it, or at least R of S T minus 1 red edges. Okay, these are the two cases that we know have to happen because n minus 1 again is this value minus 1. So we get at least edges of that many colors. Okay, so how are we going to do this? We're going to split it into cases. Well, maybe we'll do the blue case first. So let's do the case where V has at least R of S minus 1 T blue edges. We'll save room for the other case. What does this mean? Well, let's let B equal the set of W such that we have V to W by a blue edge. Now we know that the size of B is at least R of S minus 1 T. Okay? So B is a complete graph on the vertices that it has, right? If we think of it as a subset of our complete graph, we can think about the complete graph here, and we know it's at least this big. Well, what does the definition of a Ramsey number mean? Well, the definition of the Ramsey number guarantees that B as a graph has either, it's going to have a KS minus 1 that's all blue, or it's going to have a KT that's all red. That's just because it has at least this many vertices, and that's the definition of the Ramsey number. So here, in this case, we can add V to get a blue KS. Because, again, how do we define this set? It's all the things that are connected to V by a blue edge. So adding blue, V will be connected to all of these edges, so we're going to add an extra blue edge, getting us a blue KS. And over here, we already have our red KT. So we can see that, okay, we get both the cases that we needed. Okay, what we were trying to show is we either get a blue KS or a red KT, and yes, we get one of those. Okay, now we need to deal with the other case. The other case is that V has at least R of S T minus 1 red edges. And you can see how this is going to go exactly the same. Okay, we're going to let R equal the set of U such that from V to U, we have a red edge. Okay, how many things in R do we have? Well, the number of R is at least R of S T minus 1, because that's the case that we're in. That's the assumption that we made on the red edges. So what's the definition of the Ramsey number tell us? That tells us that R has either, we're going to get a KS that's all blue, or we're going to get a KT minus 1 that's all red. And again here, we're going to add V in this case, because we've chosen these guys to all be connected by V to get KT. And so once again, we've got our KS or our KT. And that proves the theorem. So this proves our bound for Ramsey numbers. No matter what, we always have a blue KS or a red KT. So the Ramsey number is at most this big. Now we saw that if we wanted to compute R33, we saw before that this bound actually tells us that it's at most 6. And so we just had to do a little example to see, oh yeah, it's exactly 6. But we'll do some more examples later on to see that this bound is helpful, but it's not always enough.